All right, it looks like we're ready to go. Welcome to day number 2 of, I call it assembly language class in my mind. We are going to be, for the first few meetings, learning some basics that we're going to need for thinking about how systems work internally. So we won't start out learning assembly language instructions, but we're kind of learning some of the foundation we'll need for that. And we're going to start out by talking about number systems and how math works at the hardware level. We won't necessarily be interested in how you might build the hardware that does this, but we want to get it at least to the point that we understand how the hardware performs these calculations, and that's going to matter even when we're working at a higher level language. If you take a look at these basic arithmetic problems, the kind of things that you probably could do in elementary school, I think you could probably do these without a calculator, especially if you had a little bit of scratch paper to work with. I think normally when they have this class on campus, students will be given a chance to work on each of these. Let's work on them together, kind of to remind ourselves of how arithmetic works. Why do we need this? Well, we're going to remind ourselves of these ideas, and then they're going to show up in the kinds of math that computers do internally. So we just want to see, kind of remember what we already know about how we perform arithmetic on numbers like this in base 10. So if you're going to have to add two numbers like this, you might write it down. Here's where you might write it down in this form where it's easy to see the place values. And then you might say, well, I've got to add each digit one at a time, or each digit place one at a time. So 7 plus 2 is equal to 9 for the low order digit. And then moving on, 5 plus 7, well, normally that would equal 12. But if we're just doing one digit, we'll represent that as a carry into the next column. And then 9 plus 5 plus 1 would normally be 15, but we can represent that as a carry into the next column. In that next column, we don't have any digits for the lower number, for the one on the bottom, but we can do what we've always done. We can realize that if I didn't write down anything past the hundreds place, that's like having 0 hundreds, or in the next column, or sorry, that's like having 0 thousands in this case. And the next column would be the 10 thousandths place. And I can pretend there's a 0 there that I just didn't bother to write down. So the next column is like 1 plus 6, which is 7. And for last column, the same idea, 2 plus 0 for just plain old 2. It may be a while since you've done it, but I think you could probably still do this stuff without a calculator. Doing it by hand, but doing it by hand, you noticed some things that you probably wouldn't notice if you let a calculator do all the work. While we were adding up these numbers, whenever we had to add a column, we had to worry about the potential of a carry propagating into the next column, into the next higher column. And when we figure out how computers do math, doing the same process in binary, we're also going to see that happen. It's just going to be happening with much smaller digit values when we write down something in base 2 instead of in base 10. We're going to be understanding the number system that computers use internally when they carry out math. And to do that, like I said, we're just reminding ourselves of how we do that ourselves, how that's done by hand when we do it in base 10. We're going to start out with something, well, we're going to start out trying to make things easy. We'll pretend we don't have to worry about representing negative numbers. You'll remember from C class, many of you probably took that last semester. In C, we can ask for at least integer types. We can ask for them in signed and unsigned form. And if we ask for them as signed values, then that, like a signed variable, can store some positive and some negative values. Whereas if we ask for them as unsigned, then it can only store 0 and positive values. Now in Java, we didn't have to worry about unsigned types. And I know in C, that was probably a new thing to start thinking about. But it's actually a much simpler way to represent and to keep up with numbers. And that's why we're going to start with that. We'll pretend we don't have to worry about representing negative quantities. We just have to worry about representing positive values. You'll remember this was on your first homework. you were asked to take a look at one of these two programs, either in Java or in C, a program that makes a variable of type short, so limited capacity, much smaller capacity than an int variable, and started out with a fairly big value, 20,000, and then double that value and then see what we get. And if you typed in this program, or if you thought about it a bit, you would see that, or you probably saw that you didn't get what seemed like a correct answer for this. And it's because, I'm sure you knew, it's because of the limitations of the type on this. Even if we were computing this at a lower level, if we were looking at what happens internally when a computer does a computation like this, it depends on getting, for this little program, getting some value for A. The way we wrote it, it adds A to itself and stores the value in B, and then we printed out B. And if we start out, at least mathematically, if we start out with a nice round value like 20,000 for A, we know the expected result should be 40,000. But if you typed in this program, or if you thought about it a bit, you probably got something that's obviously the wrong answer. In this case, you would have gotten negative 25,000 and change. In this case, this is happening because, especially using the short type in this example, we were asking this program to compute something that wouldn't fit in the type where we were storing that wouldn't fit in a short capacity int. Many of you, when you thought about this program, you probably knew this was going to overflow and you were going to exceed the capacity. And I know in the previous class, in C class, we talked about the idea of overflow and some ideas about what you might expect to see happen when an overflow occurs. This is obviously an example of overflow, but in this class, we're going to try to understand more about what's really happening when a value overflows. This may not seem like a big problem, but depending upon your application, this could result in catastrophe. One thing to appreciate is if you wrote this in Java or if you wrote it in C++, the language, C or C++, the language doesn't give you great mechanisms for noticing that this error happened during calculation. We made a variable A and gave it a value. We computed, no exceptions were thrown in Java, nothing bad, or at least nothing happened to stop our program from executing. But we got a result that was obviously mathematically incorrect. I want to say it was nonsense. It was definitely not the number we were looking for. And it would be good to have mechanisms for noticing when this happened and being able to respond to errors that happen during calculations, especially depending upon your application. Here's kind of I don't know if it's silly application. I'm going to say it's a made up application where if you had a program like this, or if you had code like this, it could result in catastrophe. Let's say you were guiding the flight of a missile and you needed to keep it a certain distance off the ground. And let's say A in our program represented that distance. So as long as you were a distance of A off of the ground, then that was sufficient. That was the minimum acceptable height. But ideally, you'd like to be twice that far. You'd like a height of 2A. Well, if A was the 20,000 in this example, and if our program computed the optimal height by doubling A, and we were expecting to get 40,000, and our program accidentally got this negative 25,000 and change, then to try to get from well, if this was a program guiding a missile, then to try to get from our current height, say, to an optimal height, we'd end up steering down to get to a height of negative 25,000, which, at least in this picture, might steer us into somewhere we don't want to be, resulting in catastrophe. Now, this is a silly example, but these kinds of things have actually happened in the real world. There's an example in 1991 of a missile defense system that failed because of a calculation error, that made a mistake because of a calculation error, and this resulted in deaths. There are a number of other problems that relate to flaws in mathematical calculations. The top one there, the 747 Dreamliner, was recommended to be rebooted every 248 days to correct from a overflow, to correct for an overflow error. And there are other examples we can find where errors like this in calculation result in programs that either are malfunction or where we have to work around known errors. To understand how this can happen and to be able to write code that can deal with this kind of thing, we need to understand something about how we'd like computer systems to perform mathematical calculations. And the ease of this, how this is going to work and how easy it is going to depend a lot on the number system we choose. First, maybe an obviously bad choice would be if computers represented numbers like Roman numerals. As a human, as a person growing up, you've probably had a lot of experience writing down things as Roman numerals or reading Roman numerals and trying to convert them to a more familiar system. If you had to do math in a system like this, I think it could present some real challenges. Like if you had to add, well, in Roman numerals, 2 plus 1, well, that's not too bad. You could kind of think of that as tally notation. So I plus I could just be I. But as you get to bigger numbers with more complex representations, xi plus v, well, there is an answer in Roman numerals. It's just going to be harder than it needs to be to get to that answer through symbol manipulation alone. That's one of the advantages of what we'll call a positional number system. This is the number system that you're familiar with. This is what you use day to day instead of Roman numerals. It's the idea that we'll write down symbols, we'll write down usually decimal digits, and the place where we write down those symbols will indicate the value of that symbol, the place value for that symbol. I mentioned, well, the system that you're most accustomed to is the decimal number system, which is in base 10. And I take for granted that you know this. We're using this as a way of trying to understand binary number systems and the way computers actually perform their calculations internally. So for a base 10 number system, you've got 10 different symbols, 0 through 9, that you can use to write down a number. And writing down multiple digits of a number, each place where you write that down determines the value of that digit. So for any place value or positional number system we look at, we'll probably have a name for it. We'll have a base that we use to represent numbers. And then we'll have digits that we can write down in that base. And the digits are always going to be 0 through whatever the base minus 1 is. Now, we're accustomed to base 10 often, even as we're playing around with other bases. We'll move back and forth between, say, binary and base 10, just because that's the system we're used to. It makes it easier for us with 2 decades or so, depending upon your age, of experience with this. It makes it easier for us to think about, probably. It's no surprise why we have a base 10 or why we've developed a base 10 number system. Developed from counting on our fingers, using those to keep up with things. And other cultures have extensions of this system, maybe with digits up to 20 for fingers and toes rather than just 10. But for this class, we'll stay with 10, at least as our point of departure for talking about positional number systems. For positional number systems, if we need to write down a number that's the base or bigger, we'll just use multiple digits to do that. And you know this, with the understanding that the rightmost, the least significant digit we write down will be worth 1. The next one we write down, the one we write to the left of it, will be worth 10 times as much. The next one will be worth 100 times as much, and so on as we write down digits to the left. Notice, of course, that every place value is a power of 10. So the ones place is secretly 10 to the 0, which is 1. The tens place is 10 to the first. The hundreds place is 10 squared, and so on up to the thousands place or the 10,000s place. So if we write down a number like 179 or 179, that means that 9 being the least significant digit, being in the ones place, is really worth 9 times 10 to the 0, or 9 times 1. The next digit, the 7 in this case, is worth 7 tens, or 7 times 10 to the first. And the highest order digit, the 1 here, is worth 1 times 10 squared. So this shorthand notation, 179, is really like a way of writing down 100, 1 in the hundreds place, plus 7 tens, 7 in the tens place, and 9 ones, 9 in the ones place. You know all of this. The reason we're reviewing it is we're trying to sneak up on other number systems that might work better computationally. If you had to design a computer, you could build it using the base 10 number system, but there might be some advantages to building an even simpler number system. When we're designing a computer system, we really have two choices for how we could design something that computes. We normally think of a modern computer as being a digital computer, but we have developed analog computing devices. Digital computing systems depend on discrete values for computing, and analog computer systems take advantage of continuous values for computing. So in an analog computer system, we might, instead of having a particular value to represent a number, we could potentially represent a wider range of numbers by maybe having a range of values to represent something. Like maybe we would represent the number 3 with a level of voltage that's near 3. So maybe somewhere between 2.5 and 3.5 volts could be our way of representing 3. A problem with this is it could have potential for errors. Why do I say that? Well, as long as your voltage was always squarely on 3, you would always be storing, or you'd always get back the value that you expect. But if you had a voltage that was kind of on the borderline between a couple of those values, you might store something that you meant to store as a 3, and you might and if it was really 3.5 or close to 3.5, when you read it back, or when some other part of your computer system tries to read it back, you might get a 4 instead if it was too close to the break between two values. And this reason, along with other maybe reasons of complexity, is why modern computer systems tend to favor digital computation. So instead of having a range of values, or instead of having potentially a continuously varying value that we use to represent numbers, we'll use discrete values. And normally a digital computer system uses just two values that it has to keep up with, or that it has to discriminate. Maybe just using off to represent 0 and on to represent 1. And if we use those two extreme values, or I guess if we use values that are easily discriminated like that, maybe there's more risk that we would store a 0 or compute a 0 in one part of our computer system and then accidentally read back a 1 in some other part of, say, our processor. So modern computer systems depend on, instead of storing ranges of values, they store numeric values based on just two discrete values, 0 and 1. So if we needed to store more values, or a broader collection of values than just a 0 or 1, how are we going to do it? Well, we already know we'll use the same trick we used in our base 10 number system, except here we'll use base 2 instead. And in a way, even though it's probably less familiar to us, it's going to end up being a lot simpler, because instead of having 10 different digits that we have to compute with, we're only going to need 2. you didn't need me to go through that little story to try to introduce you to the idea of binary number systems, but I tried to sneak up on it by comparing it to the base 10 number system we normally use and sort of some of our alternatives for how we could build a modern computer system. And internally, they represent ranges of values by putting together multiple binary digits. The way I can store arbitrary values with just zeros and ones, with just on and offs, is I'll build a positional number system out of zeros and ones, out of just a base 2 system. So just like we said with decimal, if I'm building numbers in base 2, well, my base is 2, I'll call it binary because it just has 2 values on and off. And the only digits that I need are 0 and 1. So 0 up to the base minus 1, up to 1. If I wanted to write down a number in this, I'll just borrow the same idea we had in our base 10 positional number system. It's just instead of working with powers of 10, I'll be working with powers of 2. So if I want to write down a number in binary, like the one I've got over there on the left, 1, 0, 1, 1, I'll go ahead and mention this notation. You saw this in C class, and you probably knew it before the C class even, but if I have to be clear about the base for a number, like if you just saw a number 1011, and that was all you saw, if you thought it was a base 10 number, then you might think of that as 1011. If you thought of it as base or a base as a binary number, then it would be, had to count it up, it would be 11 in binary. So to be clear about what this means, we can put the base as a subscript. So here the 2 hanging off the lower right corner of this number makes it clear that it's binary. If I was writing down a base 10 number on the same piece of paper, I could put a 10 there to make it clear that that's a number in base 10 instead of binary. All right, so if I had something like 1011 in binary, using the same ideas as our base 10 positional number system, this lowest order, this right hand 1 is really worth 1 times our base, 2 to the 0th power. Now that's still the ones position in binary, so that's worth 1 times 2 to the 0, or 1 times 1. This next one is worth twice as much. So this 1, this second lowest order 1 here is worth 1 times 2 to the 1st. Now there's a 0 in this next position. It's worth 0 times 2 squared, or 0 times 4. If there was a 1 there, it'd be worth some non-zero value. And this highest order 1 is worth 1 times 2 cubed, which is just binary, or just another word for 8. We said this on the previous slide, so just like base 10, each of the positions, each of the place values in binary is a successive power of 2, and a binary number is worth the sum of all of its bits, all of its digits, times their place value. So this, in binary 1011, if we had to know what that was in base 10, and I hope I did it right, I just did it a moment ago in my head, but if we had to carry this out, we would say, well, this 1 times 2 cubed is really 8. This 0 times 2 squared is worth 0. This 1 times 2 to the 1st is worth 2. And this 1 times 2 to the 0th is just worth 1. And if you write that here, I wrote this down in base 10, so it'd be easier for me to add it up. If you add up all of those, this 1011 in binary is really just another name for 11 in base 10. And like I said a couple of slides ago, that 10 hanging off the lower right corner of that makes it clear that that's in base 10. So, sorry for the hesitation there. The reason we're introducing this number system is we want to be able to do math in whatever number system we're working with. That's kind of the problem we started with. And we noticed even when we were working in base 10 number system, when we add up two digits, as long as we get a value that is less than the base, then we didn't have a carry. But if we add up two digits and we get a value that's bigger than, that's equal to the base or larger, then we have to carry into the next digit. And this is something that you already know. You learned this, I mean, we did this at the start of our meeting today. You learned this in elementary school. Whenever we added up two digits and the result wouldn't fit in a single base 10 digit, we had to carry into the next digit. We're going to do the same thing in binary. And in binary, when we're representing unsigned numbers, this is going to work out nicely. It's going to work out just like it did in the base 10 number system, even easier because we've only got two possible bits to worry about. This process that we go through with adding binary numbers, we're going to be able to use the same kind of process when we switch to working with signed numbers. Sorry, I should have said, this is going to be pretty basic when we don't have to worry about negative numbers. But eventually we're going to sneak up on a way of representing numbers, including positive and negative numbers, that lets us follow similar rules for adding binary representations, even if one of the numbers might be negative. We're going to have to try to figure out a good way of representing signed numbers that makes basic arithmetic operations easy. We just don't have to worry about that today. Today, we're only worrying about unsigned values. So we only have to worry about adding up stuff that's zero or positive. But that example that we looked at earlier, the example from your first homework, shows that a poor understanding of what might happen when overflow occurs, or if you add values where the result doesn't, where overflow occurs, where the result doesn't fit in the type you're using to represent those values, can lead to catastrophe or other security vulnerabilities in a problem, in a program. So let's figure out how to add numbers that are in binary. Now, in base 10, up at the top, when we had to add decimal numbers, like we just said, if we added two decimal digits and we get a result like 7 plus 2 adds or sums to 9, so we get a result that fits in a single decimal digit, a result that is less than our base, then in this case we only need one digit to store the result. But like this case over on the right, if we add 7 plus 5, that adds up to 12, which is bigger than, which is equal to or larger than our base. It won't fit in a single digit. So the way we've handled this in base 10, the way you handled it from elementary school, is we carry 10 of those, or we take 10 of that result and carry it into the next digit position, next place value, which is worth 10 times as much anyway. And we just keep what's left over. In this case, if 7 plus 5 is equal to 12, we carry 12 of that 10 into the next digit, and we keep 2 for the lower order digit. How does this work in binary? So we're accustomed to this in base 12, or sorry, in base 10. How does this work in base 2? Well, fortunately, a lot of cases don't result in a carry in base 2. If you add 0 plus 0, even in binary, that adds up to 0. If you add 0 plus 1 in binary, that adds up to 1. Well, that's still less than the base, still less than 2. If you add up 1 and 0, same thing, you get 1. So the only place where a carry happens is where you add a 1 and a 1. In that case, that adds up to 2. So we'll do the same kind of trick we did in decimal. We'll carry 2 over into the next digit position. Sorry, so 1 plus 1 equals 2. That won't fit in a single digit. So we'll carry 2 into the next digit position. Well, just like this position is worth 10 times as much as the previous one in decimal, this binary position is worth 2 times as much as the ones place in binary. So when we carry 2 into the next most significant digit, we just have to write a 1 down as the carry. And once we've moved the carry, once we've taken 2 and put it into the next column, we're left with 0 in the ones place. I feel like I did a bad job explaining that. We'll get some practice. Any questions before I try to move on and let us work through an example or two? All right, I hope some people are there. In base 10, as we added digits, we always had to keep up with whether a carry happened in the next digit. If we were adding multi-digit binary numbers, we would be doing the same thing. So I came up with an example of 2 4-digit binary numbers that we're going to add using the rules that we just talked about and keeping up with how the carry might propagate into the next digit. So we've got 1011, which we already figured out in base 10. That's that's equivalent to 11 in base 10. I got another copy of the same number down here. So also 11 in base 10. We know in base 10, those should add up to 22. Let's see what in base 10, they should add up to 22. And let's see what happens if we try and add them in binary. So if we take 1 plus 1 in binary, well, that was the case we just talked about. That adds up to 2. Well, we can't store a 2, so we'll store a 0, and we'll carry that 2 into the next bit position. So just like in base 10, this blue one up here represents a carry into the next bit position. In binary, that'd be the 2's place. Well, in this column, we've got 1 plus 1 plus the carry we just carried over. Well, that adds up to 3. Well, 3 is bigger than the base. So we'll carry 2 of that 3 over into the next bit position. So I wrote down a 1 up here as the carry. And then when we carry that 2 over into the next bit position, we still have a 1 left over in the bit position we were adding. So again, said real fast, this 1 plus 1 plus 1 adds up to 3. We can't write down a 3 here because that's bigger than our base. So we'll take 2 and carry that over into the next position, leaving 1 for this bit position for the 2's place in binary. Continuing on to the next column, 1 plus 0. So this column right here, 1 plus 0 adds up to 1 without a carry. That one fits into that current bit position. 1 plus 1, we didn't have a carry into this last bit position. So we just have 1 plus 1, that adds up to 2. We can't write down a 2, so we'll carry 2 over into the next bit position. Subtracting off that 2, we're left with 0 in this bit position, and then 1 carried into the next bit position. So in binary, that gives us 1 0 1 1 0, adding up each of the bits and carrying into the next bit position where we have to. We already worked out in decimal, this should be equal to 22. Is that right? Is this, do we get the right answer? Is that binary for 22? Well, we already went through how to convert from binary to decimal, so we could just do that and check it. We got one more bit position than we had when we did this earlier. But let's work our way from the low order bit to the high order one. This 0 in the low order position is 0 times 2 to the 0, plus 1 times 2 to the first, or 1 times 2 to the first is 2, plus 1 times 2 squared, or 1 times 4, plus 0 times 2 cubed, or 0 times 8, plus 1 times 2 to the fourth, or 1 times 16. So if we add all of those up, 16 plus 4 is 20, plus another 2 is 22. So yeah, we were hoping, or at least decimal told us we should get a result of 22. And when we checked the binary, it looks like we got the right result. Getting a little more practice converting from binary back to decimal. So it looks like our scheme for adding up numbers, even when they're in binary, gives us the same result we would expect for if we did this in decimal. Questions before we try to move on?
Is there a formal name for that expanded out representation of the base?
You mean like what I've written out here?
Yeah, the multiplication part of it. I mean, it was just a question on top of my head because seeing it represented so much.
I think there is. I think we're going to talk about digit reduction as a way of converting from base 10 into binary in a moment. And I think this is a related term. I apologize, off the top of my head, I'm not remembering what it's called, but I think it's in a later slide, so I think it's going to come up.
I think
someone else started
on the previous slide.
Pardon, it's on the previous one?
Is this the name? Oh, true positional format? Or not really?
Positional form. I don't think of that as a term. The true positional format. I guess I would look at that and say, oh, this is like an exhaustive way of notating what you mean here. I don't know if that's really a term. Usually terms are going to be in italics here, and that's looks more like Comic Sans. So I don't know. I think of that as informally saying this is showing what that binary representation really means. Give me a moment and it may show up in our slides. I apologize. I give myself a B- on my answer to your question there. Other questions? All right. So here's what I think we've done so far. I tried to convince you of this, that you already know this idea of positional number systems, and we can reuse what you know in other bases. And we did addition, both in base 10 and now in the less familiar base 2. We just did a trick of converting between bases. To check our answer, we just used the definition of a positional number system to convert from binary into base 10. We did it with this example. So we just thought of or wrote down what a binary representation means. And then if we expand that in base 10, if we just do that math in base 10, that'll give us the value of a binary number in base 10. So I'll try and say this real fast. If this number means 1 times 2 to the 4th plus 1 times 2 squared plus 1 times 2 to the 1st, we can just add that up in base 10 to know that that's binary for 22. We could even write this in shorter format by just wherever we've got a 1. Since binary only has zeros and ones, we could just write down the place value for that and add up just the digits, add up just the bits where there's a 1. And in this case, we'd of course get 22 again. What if we had to go the other way? What if I gave you a number in base 10 and I asked you to convert it to binary? Well, you could use a similar trick. You could say, well, I've got this number 22 in base 10, and if I had it written down in binary, if I put a 1 in the highest order position, that'd be worth 1 times, well, in this case, let's say I'm going to try to convert it to a 5-bit binary number. If I wrote down a 1 in this highest order, oops, sorry, I said a 5-bit number, but really I've got 6 things written down here. So let's say I tried to convert it to a 6-bit binary number. If I wrote down a 1 in this highest order position, that'd be worth 1 times 2 to the 5th. If I wrote down a 1 in the next bit position, that'd be worth 1 times 2 to the 4th. So I could just figure out where I need to put the ones, working my way from the highest order to the lowest order. For the highest order one, if I put down a 1 there, that'd be worth 1 times 2 to the 5th, or 1 times 32, or just plain old 32. Well, that's already bigger than the 22 I wrote down, so there must not be a 1 there. There must be a 0 there. I can keep working my way to the next highest order bit. So there's not a 0 in that, in this case, in the 2 to the 5th position. How about the 2 to the 4th? If there was a 1 there, it'd be worth 16, and 22 is bigger than 16, so there must be a 1 there. So I can write down a 1 there, that's worth 16. Out of that 22 minus the 16, I've got 6 left over. So if this bit accounts for 16 of that 22, there's 6 to be accounted for by the remaining bits. So minus taking the 22 minus the 16 that's represented by this bit, I've got 6 left over. If I put a 1 here, that'd be worth 8, which is already bigger than my 6, so that must be a 0. If I put a 1 in this next position, that'd be worth a 4. Well, my 6 is bigger than a 4, so I better write down a 1 there. I must have a 1 in this position, or I'm not going to be able to add up to as much as 6. So there must be a 1 in this 2 squared position. That accounts for 4 more of that number. So I started with 22, a 1 in this bit position is worth 16, a 1 in this bit position is 4. Now I got 2 left over. If I move down to the next bit, that's worth, if I put a 1 there, that's worth 1 times 2. Now the number I've got, what I've got left is 2. So there must be a 1 there. Again, that's worth 1 times 2 to the first, or 1 times 2. That leaves me with just 0 left over. So there must be a 0 in this lowest order bit. So I can convert a decimal, or one way to do the conversion is to work from high order bit positions to lower order ones. Wherever the bit position would be worth more than the number or more than what's left over in the number, you have to write down a 0. Wherever it would be wherever that bit position is worth whatever's left of the number or more, sorry, whatever's left of the number or less, then you have to write down a 1 and then take whatever's left, subtract that value from the number and take what remains and use that to fill in the remaining bit positions. And over the last few slides, I tried to show how to do this. In this case, if we wrote down this number as binary, we would get 0, 1, 0, 1, 1, 0, which hopefully is binary for 22. This looks a lot like the number we had a couple of slides ago, except it's got this extra 0 out in the high order bit position. Does that matter? Well, like numbers in base 10, writing extra high order zeros doesn't really change the value of the number. So we could just ignore this high order 0 in this bit. And sure enough, that's when we did this conversion in the other direction. That's exactly what we started with in binary to get 22. So I'm going to say our conversion worked out correctly. We just ended up with an extra high order 0 that doesn't really matter, at least not for unsigned numbers. For signed numbers, we're going to see that those high order bits can matter. And the number of bits, like here, backing up a couple of slides, we just started by trying to write this out as a 6-bit binary number. And we realized pretty quickly that we didn't even really need this high order bit. It ended up having a value of 0. But when we start representing signed values, the way we're going to end up representing them, it will matter how many bits we decide we're using. And zeros in high order bit positions will end up mattering for how we interpret that number. Questions before we move on? So the new thing that I think we've learned is we learned how to do the conversion the other way. We learned how to, kind of based on the definition of binary, we kind of got conversion of binary to base 10 for free. We just have to write down what the definition of binary numbers means, and it tells us how to convert them to base 10. Converting the other way, we could kind of do that. You could think of it a little bit as trial and error, working our way from the high order bit positions and always writing down a 1 where we needed to reach whatever magnitude we're trying to represent. I guess the next thing we might want to do computationally is subtraction. We would want to figure out how computer systems could do subtraction. Well, later we're going to see that we're going to learn how to do subtraction directly ourselves. And computer systems could be built to do that, but eventually we're going to figure out how subtraction works. Eventually, we're going to figure out an easier way to do a subtraction, or to get subtraction almost for free based on how we're going to represent positive and negative numbers. A computer system could have a subtract operation. Like if you wanted to compute C equals B minus A, you could have a machine instruction that just says subtract B from A and store the result in C. Or if you already had a pretty good way of representing negative numbers, you could get by just using addition. You could say, well, A minus B is really the same as A plus negative B. And we're going to end up with, eventually, we're going to end up with a representation that gives us that as at least an option for doing subtraction. Why would we want to do that? If we could get subtraction for free by adding a negated version of the number, it potentially makes our hardware simpler. We don't need to build hardware to do addition and then more hardware. And when I say build hardware, I mean we don't have to create logic on an integrated circuit to do this. We could just reuse existing circuitry. For now, we're going to figure out how to do subtraction ourselves. And just like we did with binary, the trick that we're going to do, the trick we're going to learn to do subtraction ought to work on any base. It's going to, just like at the addition we just did, our rule would be we take two digits, we add them up. If they're less than the base, we can write down the result directly. If they're equal to or greater than the base, we have to carry something into the next digit and then leave what remains in the current digit. We're going to learn the same trick or the same idea for subtraction, and what we try to do should work for any base. Now, if we're doing this in decimal, you remember how subtraction works. If we were subtracting a number like 7 from 85, well, if we started with the ones place, we can't directly subtract 7 from 5 because in the ones place it's not big enough. But you know how we do this in base 10. We borrow from the next digit. And we're going to end up doing the same thing in binary. Now, a number like 85 is, in a positional number system, is just is a representation for 8 times 10 to the first plus 5 times 10 to the 0th. Minus 7 is minus 0 times 10 to the first, and 7 times 10 to the 0th. Like I just said, we can't directly subtract 7 from 5 because 7's too big to subtract from 5. But just like you did in elementary school, we're going to handle this by borrowing from the next column. The next column's worth 10 times as much in base 10. So when we borrow from that column with the 8 in it, we're really borrowing, at least if we want to borrow from the next column, we can say, well, pretend that 8 is a 7, or steal 10 units from that column with an 8 in it. That's going to take the 8 down to 7. And it's going to give us over here in the ones place, it's going to give us an extra 10 to work with. Now, the way this is written down is you can think of these top 2 rows as what you're subtracting from, and this bottom row is what you're subtracting. So you're still taking 7 away, but not just from the 5, but the 5 along with the 10 you borrowed from the column to the left. When you borrowed that 10, well, that 8, you took 10 from it. It was previously 8 times 10 to the first. Now, since you took 10 from it, it's only 7 times 10 to the first. So I decreased this column by 1, but I got 10 to work with over in the ones place. And then when I subtract, now I've got 5 along with the 10 that I borrowed. When I subtract 7 from that, well, these two together are worth 15, minus the 7 leaves me 8. And then back over in the next column, well, 7 times 10 to the first minus 0 times 10 to the first leaves me 7 times 10 to the first. So the result of 85 minus 7 is 78. You didn't need to do that in base 10, but we were warming up to do the same thing in binary, in base 2. So what if we had a subtraction problem like this in binary? 100 minus 001. Now the top line is binary for 4, and the bottom line is binary for 1 in base 10. This top guy is 4, and the bottom one is 1. Obviously, I can subtract 4 or 1 from 4, but if you look at the individual binary digits, we have the same problem. I can't subtract a 1 from a 0 without borrowing. So I need to be able to do the same trick in binary. It's just in this case, I guess I would say we're going to have to borrow 2 at a time rather than 10 at a time. So this top number, if I had to write that down in same term we were asking about before, true positional form. So I'm going to say that's going to be our term for this expanded exhaustive format here. Even though I apologize, I wasn't sure about that before. So this top line is really 1 times 2 squared plus 0 times 2 to the first plus 0 times 2 to the 0th. Same kind of thing for the next line. The reason to expand it like this is to see how we can do borrowing in binary. Because I can't subtract a 1 from a 0. But if I had a 1 in this bit position, I could borrow from it. Well, I have a 0 here. Now this 1 in this bit position is worth 4 times as much as this. So I'm going to borrow from this bit position so I can subtract in the 1's place. Now this 1 in this bit position is really worth twice as much as what's in this bit position. So if I borrowed from this 1 here, just like we did in base 10, well, if I borrowed from it, that 1's going to become a 0. And since it was worth twice as much as this bit position, that's like having 2 to work with in this bit position, in the 2's place here, if you were talking in binary. Well, if I want to write this down in binary, instead of putting a 2 there, I could write it down as a 1 0 in binary. I don't really mean base 10. 10, I mean the binary number 10, which is just binary for 2. In fact, it might be better to write this down as you've got 1 2 to the first, and you got another 1 2 to the first, so we don't have that confusion. So when I borrowed 1 from this column, I got 2 1's to work with in this column, because the 1 in this column was worth twice as much as this column. Well, the whole reason I started borrowing is so I could subtract this 1 from this 0. So I can do the same thing again. Now I got 2 1's to work with in this column. I can take one of those, borrow from it, and now I've got 2 1's in this rightmost column. Again, because the 1 times 2 to the first is worth 2 1 times 2 to the 0's. So I wrote it down twice. So again, you can think of these top 4 lines is what I'm subtracting from. I scratched some of them out as I was borrowing. And this bottom line is what you're subtracting from it. But now that I've done all this borrowing, I can finish this problem. I haven't changed the top value, but now I can subtract 1. If you're subtracting 1 times 2 to the 0 from, well, 2 1 times 2 to the 0's, you can take away one of them, and that leaves you with 1 times 2 to the 0. Moving into the next column, you've got 0 times 2 to the first that you're well, let me say that the other way. You got 1 times 2 to the first, and you're subtracting 0 times 2 to the first from it. So that leaves you 1 times 2 to the first. Over in the topmost column, well, you borrow it out of here. So all you've got left is 0 times 2 squared but you're only subtracting 0 times 2 squared, so that leaves you 0 times 2 squared. Or if you had to write that down in short form or in normal form in binary, 1, 0, 0 minus 0, 0, 1 leaves you 0 in this highest bit, 1, 1 in the remaining 2 bits. So what we just calculated down here in shorter form. If we had to convert this to base 10 to check it, well, we already said this top one is 4 minus 1. In binary, the 0, 0, 1 is, that's worth 2, that's worth 1. So this binary number is 3 in decimal. And that's what you'd expect. 4 minus 1 should give us 3. We just went through a kind of a long trip to borrow across multiple digits. It's just 3 digits here, but when we were subtracting a 1 from that low order 0, we had to move 2 digits to the right to borrow from it. And in binary, there could be a lot of cases where we have long strings of zeros that we have to borrow from. So we may have a lot of cases like this. Like, let's say we were subtracting from this lowest order bit. Well, here, let's say we're subtracting a 1 from this lowest order bit. We might have to borrow from several digits away. I apologize because I started talking about this number as if it's binary, but you can see from this, we really mean for this to be a base 10 number. The same thing can happen in base 10, maybe it's just not going to happen as often to us. If you had to subtract a 1 from this, you'd have to borrow from a digit several digits away. In base 10, we could simplify this by saying, well, whenever you have to do that, you can think of this number as 9s in all of these low order positions. You could replace all these zeros with 9s, and that would get you almost all the way up to 1,000 in this case, plus 1 more to get you all the way up to 1,000. Whenever we have to borrow across multiple digits like this, we can use this same trick in binary. I feel like I said that badly. Let me try and say it one more. If we have to borrow from this 1 multiple digits away, we can think of having a shorthand rule that this 1, 0, 0, 0 is really worth the same thing as 0 with 9s in place of all of those zeros, plus 1 more to get us all the way up to, in this case, 1,000. How does this help? Well, if we were doing decimal subtraction, we could rewrite this 1,000 as 999 plus 1. And then when we're subtracting this 625 from it, all of these 9s are going to be easier to subtract from because we've gone ahead and borrowed from this 1 over here on the right. Once we've done that, we can subtract all of these lower order digits without having to worry about doing the borrow as we're doing subtraction. So in this case, 9 plus 1 more is 10, minus the 5 gives us 5. 9 minus 2 gives us 7. And then the next 9 minus 6 gives us 3. So it's kind of like we planned ahead for the borrows that were going to happen. We can do the same thing in binary. And that's what I tried to say a moment ago. Whenever we have a 0 minus something that's bigger than 0, we can go ahead and borrow from the next non-zero digit, putting, well, the binary equivalent of 9, which would just be a 1 in place of that 0, plus 1 more 1 in the lowest order position. Now here's kind of the simplest case where that would happen. So if we were subtracting this 1 from 0, we could rewrite this 1, or we could borrow from this 1 and rewrite it as the binary equivalent of 0 with a bunch of 9s after it. Well, here that's going to be 0 with, well, 1 smaller than the base, so just a 1 here, plus 1 more 1. So this is equivalent to this 1 in the next higher position. And then once we got the two ones up here, we can subtract this one from them. So 1 and 1 minus 1 gives us a 1. In the next position, well, now we've got a 0 there. To subtract a 1 from it, we can do the same trick. So we'll rewrite this one as 1 plus 1 in this column. And then 1 and 1 minus 1 leaves us just 1. In this next column, we already borrowed a 1 from that. So 0 minus 0 is 0. In the next column, 0 minus 1, we'll have to do the same trick. We'll rewrite this 1 or this 0 as two 1s. Sorry, that was an accidental phone call. I assume you heard that. So these two 1s minus a 1 leave us 1. And then in the highest order column, we already borrowed from that. So we have a 0. 0 minus 0 leaves us 0. We could check this in base 10. If we convert this number back to base 10, we get 11. And since we're familiar with that, yeah, 22 minus 11 should give us 11. So we did an example of subtraction in binary. I guess comparing it to subtraction in base 10, in binary, you may feel like you're having to borrow across multiple digits more often because it's common in binary numbers, just because we only have zeros and ones, to have potentially a bunch of zeros in a row that you might have to borrow through. So that trick we just did could come up more often. We've been working in binary. Sorry, I'm secretly trying to sneak up on the idea of hexadecimal here. Internally, computer systems use a base 2 number system. We started with the idea that it's easier to represent discretely. And even though it took us a little getting used to, it's easier to perform math because you've only got a simpler set of rules. You've only got a few cases that you have to worry about. But writing down and copying and talking about binary numbers is difficult for humans because they end up being long strings of zeros and ones. Which is why, and we said this in the C and software tools class already, for binary numbers, we often represent them in base 16 as hexadecimal numbers instead. Like we said in that class, think of hexadecimal as a shorthand way of representing binary numbers, where instead of representing them just 1 bit at a time, instead of as a string of zeros and ones, we're going to represent them 4 bits at a time. And that'll give us a much more shorthand way of writing down binary numbers 4 bits at a time instead of 1 bit at a time. In hexadecimal, we're going to have a rule for representing every possible combination of 4 bits. So 4 zeros in a row, it's going to be represented by 0 in hexadecimal. All ones in a row. 4 ones in a row, we're going to represent, well, that in binary, that's represented by 15. We're going to have a single hexadecimal digit for that. So let's talk about hexadecimal. You already know this from the C and software tools class. It's another example of a positional number system, so we'll get to reuse what we've been talking about. Hexadecimal is just going to be base 16 rather than base 2 or base 10. That means we need digits for 0 up to 15. And well, if we're borrowing from a base 10 number system, we run out of digits after 9. At least we run out of symbols for that. So for hexadecimal, we're going to need a symbol for like I said a moment ago, for every possible bit combination for 4 bits. If we wrote them down in order in binary, counting up from 0000, 0001, all the way up to 1111. If we converted each of those to decimal, then each of them represents a different magnitude in decimal. For instance, 1011 is worth 11. But if we had to write down a symbol for these, we run out of decimal digits after 9. So for hexadecimal, we'll use the first 10 decimal digits, 0 through 9. And then, as you know, we'll start using letters after that. So to write down a single symbol to represent 10, we'll use A. B will be our name for 11, C for 12, D for 13, E for 14, and F for 15. As long as you remember this table, converting from binary to hexadecimal is going to be really easy. And it's the same thing we did in C and Software Tools class. If I had a big binary number like this, I could take it 4 bits at a time. Here it's easy because it's 12 bits, it's a multiple of 4. If say you didn't have, say you had bits written down that wasn't a multiple of 4, you can always start from the low order bits and say, well, the 4 lowest order bits are my low order hex digit, and then continuing the next 4 bits are my next hex digit, and my next 4 bits are the next hex digit. The reason I'm making a big deal out of this is, let's say this bit was a 0 instead of a 1, and someone didn't bother to write it down. If you started from here, you'd have some leftover bits at the end. If you start from the low order bits, then you can always assume high order zeros for missing bits on the high order end. Here, it's easy for us because we're assuming, or because we started with an example that's a multiple of 4 bits. All right, enough stalling. These top 4 bits are 1100. If we look at our table, well, that's binary for 12, and that is represented as C in hexadecimal. So that 1100 is C in hex. That next one, 0101, well, that's 5 in binary. And for that, we just get to use the decimal digit 5. So the next 4 bits are represented by 5. The low order 4 bits, 1110, well, that's worth 14. And in hexadecimal, we say 14 by saying E. So that hexadecimal number, 1100, 0101, 1110, we can say in much shorter form as C5E in hexadecimal. As a number system, as a positional number system, hexadecimal follows the same rules as our base 10 and our base 2 number system. Every hexadecimal digit is worth whatever that digit's face value is times some power of 16. So A7 in hexadecimal is worth A times 16 to the first. Now that A is really just another word for 10, plus 7 times 16 to the 0. So if we wanted to know what this was in base 10, we could just add it up doing our math in base 10. So 10 times 16 to the first is just 10 times 16, or 160. 7 times 16 to the 0th is 7 times 1, or just plain old 7. So that A7 in hexadecimal is just another word for 167 in base 10. If we had to go the other way, we could use the same kind of trick we did when we were converting from base 10 into binary. We could say, and starting with the same number, 167, if we wanted to know what that was in hexadecimal, we could say, well, if it was a 3-digit hexadecimal number, so here we're pretending that we didn't just convert in the other direction. So let's say this could be a 3-digit hexadecimal number. Whatever's in this top digit would be worth something times 16 squared. Well, even 1 times 16 squared is 256, so that's already too big. So that must be a 0 in the 16 squared place. So I wrote down a 0 there. That leaves us 167 to be taken care of by the next 2 hexadecimal digits. Well, here we could do a little trial and error. 10 times 16 to the first, or 10 times 16 is 160. 11 times 16 to the first is 176. Well, 176 is too big. It's bigger than the number we're converting. So it must be 10 times 16 to the first. So the next hexadecimal digit must be 10, or must be A in hexadecimal. That accounts for 160 of that 167. What's left? Well, that leaves us just 7 remaining. So there must be 7 in the ones place, or 7 in the 16 to the zeros place. So 7 must be our lowest order hexadecimal digit. That gives us a way of converting from decimal to from base 10 to base 16, decimal to hexadecimal, by starting with our highest order hexadecimal digits and working our way to the lower order ones. If you took the C in Software Tools class, you probably remember a way of converting that goes the other way. You ought to be able to use either of these in this class. That is, you ought to feel comfortable converting using either technique. When we did the same thing in C class, you may remember we would take a number, we could mod it by 16 to find out what the lowest order hexadecimal digit was. And then we could divide by 16 to effectively slide all the hexadecimal digits in the lower order direction. And then we could just keep doing that until we accounted for the whole number, until we reached a value of 0. And you could try this yourself. This should give us exactly the same result we just got using the reduction of powers method. And I don't think I've said this term before. I mentioned it when I had a question, but this way of working our way from the high order digits, whether they're binary or hexadecimal, toward the lower order ones, we'll call that reduction of powers as a way of converting from base 10 to hexadecimal or whatever base. Now, if we had to do math in hexadecimal, we can do it using the same tricks that we did when we had to do this in binary. It's just, or when we do base 10, it's just every digit has a lot more possible values in it. But the techniques are going to be the same. So if I had a hexadecimal number like 7A and I had to add 5E to it, I could do the same trick. I could start with the lowest order column, working my way toward the higher order columns, carrying when I have to. What's A plus E, this lowest order column? Well, I could cheat. Maybe cheat is too strong a word. I could make that easier for myself by temporarily switching over into base 10. I have to add A plus E. Well, consulting my table, A is just another name for 10. And E is just another name for 14 in base 10. And I know how to add those in base 10. 10 plus 14 is 24. So I just have to write down whatever 24 is in hexadecimal. Well, 24 is too big. There's no single hexadecimal digit for that. But I could subtract off 16 as a carry, and that would leave me 8 for that lowest order hexadecimal digit. So A, which is just another name for 10, plus E, which is another name for 14, equals 8, with a 1 carried into the next hexadecimal digit. And that 1 being worth, or with a carry into the next hexadecimal digit, and that carry being worth 16 ones. Well, then I could work in the next column. So I've got a carry of 1 plus 7 plus 5. Well, here it's kind of easy for me. 7 in hexadecimal is just another name. It's the same as 7 in base 10. 5 in hexadecimal is just another name for 5 in base 10. So 5 plus 7 plus a carry of 1 gives me 13. Well, 13 is less than my base. So I don't have to worry about carrying. I don't have to worry about subtracting off 16 for a carry. And 13 in hexadecimal is just another name for D, or I guess in hexadecimal, D is what I write down for 13. So 7A plus 5E is equal to D8 in hexadecimal. What if I had to do subtraction in hexadecimal? We'll see if we can get through this example, and I may have to cheat and record a little bit of this lecture on a separate short video. All right, let's give this a try. So let's say I had D8 minus 5E. Well, 8 minus E. 8 is, if I wanted to convert to base 10, just to make this easier, 8 is another name for 8 in base 10. E is another name for 14 in base 10. I can't subtract 14 from 8, but I can borrow from the next position. So I'll take that D and I'll borrow 1 from it. That's going to make the D, it's going to decrement it, it's going to make it a C. But since it was worth 16 times as much, that gives me an extra 1 0, an extra, and that's hexadecimal for 16. That gives me an extra 1 0 in the ones place. Falling back to cheating in base 10, well, now the 8 is still worth 8. The E I'm subtracting from it is worth 14. But the 1 0 that I borrowed in hexadecimal is worth 16 in base 10. So 8 plus 16 minus a 14 gives me 10 remaining, and 10 in hexadecimal is A. So I get A in the low order hex digit. If I move to the next digit, I've got to compute C minus 5. I can hop over to base 10 to do that. So that C is another name for 12 in base 10. The 5 is another name for 5 in base 10. 12 minus 5 is 7. And in 7, I can write that down as just a plain old 7 in hexadecimal. So D8 minus 5E is 7A in hexadecimal. And that gets us almost everything we need to talk about for today. I'm out of time, so I'm going to end the lecture here. You've got a homework that you have to do for Wednesday that requires our one last topic of overflow. I'm going to split that out into another short lecture that I'll post shortly after this lecture, but I'll go ahead and end this one now, and I'll add hopefully a short video after that to help you out for that homework. Let me stop recording here, and then if people want to hang around and ask questions, I'll take those right now.